Yeah, so before starting the lecture, I have already written the overview over here. So this is what I'll try to cover. I don't know time. Okay, so before starting the talk, I wanted to say something about the history of the Markov. Of course, this Markov chain dates back to 20th century, earlier 20th century. The study was given by Markov, and later many mathematicians used it, and even now it is being used heavily in probability. So while searching for these things in internet, I found this nice thing which I would like to share with you. So Markov used this Markov chains and to study the distribution of vowels in Euclid only, which is something written by Alexander Pushkin, and it was very different for me because studying vowels in a textbook is quite not normal. Okay, whatever. So let's start with a bit of motivation first. As I've already written in the abstract about how Markov chains has this philosophy of depending on the present and forgetting on the past. Okay, so let us draw this thing. This is a lily pad, and there is this frog. So this frog is not sure in which lily pad to stay. So he is jumping from here to here with probability p, and he is staying here with probability 1 minus 2, and from here he is staying here with probability q, and so that's 1 minus 2, and he is moving with. So what is happening? He starts from one of the lily pads. Let's name this 1 and this 2. So let's say he starts from 1, and now he tosses a coin, biased coin, with p probability to be head. And if head comes, he moves. If tail comes, he stays. And this continues. He continues to do that. And we will use this thing to define Markov. So we will look at some properties of it. So what are the important properties that you can observe? Once you are at 1 or 2, whatever happens in the future is only dependent on 1. So let's say he followed some steps 1, 2, 3, 1, 1, 2, 1, 2, 1, 1, 1, 2. But once you know that at the end of time he is at 1, you know that with p probability he will be at 2, and with 1 minus p probability he will be at 2. So once you know the present, you know the future. Not exactly, of course, but you at least know the distribution of the future. So that's how we will define Markov chain. So firstly, I will take this sequence of random variables, and each of these random variables, or rather random objects, because this might not take real values, and these things take values from this space. This is the state space. Okay, first of all, is the font okay? So this is a sequence of random variables, and I am looking at this. So what is this saying? I know everything about the past. So this is the past that has happened, and I also know what is the present. Now what does this thing say? Even if we know the past, the information that we have from past is completely irrelevant. So only this thing is enough to determine the, or rather probabilistically determine the future. That is. So this is the definition of Markov chain. Any sequence of random variables or random objects taking values from this state space with satisfying this property is called a Markov chain. Now in some Markov chain that we will be going to use everywhere in our talk, it so happens that this probability doesn't depend on this end step, and that happens here also, because if you come here at the first step or at the third step, the probability that you will move here immensely and probability that you will back to here, again remains 1 minus p. So it doesn't depend at which step you come. So I can write this as p x comma. So this is just a notation. And once you write this as p x comma y, this gives you a power. Now you can write this thing as a matrix. You will list out all the possible values from x and again from x, and now you will write the each probability that will be given values. And this matrix is known as the transition matrix. And this thing actually determines the Markov chain to some extent. Yeah, so now let us discuss one typical property of this Markov chain, the transition matrix. So this thing is a probability distribution, right? So if I sum over all y, and I have taken this state space to finite. So whatever we are going to discuss today will be finite only more or less, except some counter cases. So this thing, if we sum over all y, all possible y, what will be this thing? This is just a probability distribution, hence 1. Hence, if I sum over all y, this will be 1. And hence, if I sum over all these row values, it will be 1. So the row sum is 1. Or in other words, T1 is just 1 is the vector of all ones. So this is a nice property of
just a clarification for this lily pad situation, right down the transition.
yeah. So here there are two possible values, 1 and 2. 1, 2. So from here 1 to 1, what is the probability that you will keep at 1? And you know the sum is 1, so it has to be. And from 2 to 1, we will move with probability. And you know the sum is 1. And you can see that this is a, so for some Markov chains, this thing is, this thing holds that it doesn't depend on it. It's called homogeneous Markov chain. For every example we are going to discuss, it will be homogeneous. So whenever I say Markov chain, it will be homogeneous. Yeah, now I will discuss some types of Markov chain. So firstly, now let us again take this lily pad example, but I am just not drawing this lily pad again, I am just denoting with points. And you go from here to here with probability, return to here with probability minus c. Same goes for this thing. And now I will add an extra point, let's say another lily pad, and from here you go here with probability 1. So once you are here, so if you start from here, you will never return to here. So this seems to be useless thing, because once you start from here, you will go somewhere here and then you will continue moving here. So those Markov chains are not good to study. So we want some good Markov. So how are we gonna discuss that? So we will take for all x and y from x, I will have this thing. So what does this say? So once if I choose 2 points from the state space, I know that after some time, if I start at x, after some time, I will eventually reach y with some positive probability. So I am not saying that it will reach definitely, but it will have some positive probability. At least there is a chance of reaching. So here you can see that this Markov chain is not irreducible, but that one was, because from here you can of course reach here, from here you can of course reach here after some steps, and there exists some positive R such that you can reach. So you will see that irreducible Markov chains have some nice. Okay. And now let's discuss another Markov chain, just to see the irreducible case more nicely. The name is right there.
R should be greater than.
Which one?
Probability should be greater than R.
Right. No, I will not say the probability is greater than R. I am just saying that after there exists some R such that after R may there is a positive probability that you will go from X to 1.
That is the definition of an
Irreducible. Yeah. Because that imposes some kind of limitedness in the structure. Okay, so let's take this graph, or you can just consider this to be some points, and from here, it is as if someone is sitting over here, and he moves here with probability half, and he moves here with probability half. And same for 1, same for 2, I am not drawing the arrows. So what happens, you can see that this is irreducible. This is clear because you can just go from 0 to everywhere and from 2 to everywhere, 1 to everywhere with some positive probability. So this is irreducible. But here what happens is, just look at the times when it can actually return to 0. So it can return to 0 at, can it return to 0 at one step? No, because at one step it will either move 1 or 2, 5. So it cannot return to 1 at one step. Can it return to in 2 steps? Yes, it can. 3 it can. So it can only return in even number of steps. So this kind of imposes a periodicity, or it only returns in some period of intervals rather than some after each interval. So it will never return to 0 with positive probability in one step. So this kind of imposes a periodic structure. So that's why we are going to define something called the period of a state. Here's this thing, and I define what is the period of a state. Again, there will be a lot of definition at the beginning, but I will move to some nice examples. So, what is happening here? I am looking at the time at which they can return to its original. So, tau of x, I take this x to t returns in 0 such that probability x t equals to x where x naught equals to x. So this is the set of all times at which it can return to x with some positive probability. And for 0 it goes to 4, 6, 8 and all these numbers. And I take the period to be the GCD of this. That is the period of the state. And what happens for irreducible chains, now you will see why I define irreducible chains. For irreducible chains, for any xn1, the period is same. So this is a nice proof again, but I am not going to discuss the proof. But you can see that it has a nice intuition because it has some probability that it will go from x to y, and then with some number of steps it will again come back to x, and hence this 2 will be equal for any x and y. Now once you know the period is same over all x and y, you can define something like the period of the chain. So let's define period of the chain. And it's just the period of each of the points of the stress test. And if the period of the chain is 1, then it's called equilibrium. Now you can see that this one is irreducible. It has all the periods same, and it's not irreducible because the GCD is 2 here, 2 here, 2 here, and the period of the chain is 2. Hence, it's not irreducible. Okay, any doubts?
The periodicity of a chain is not defined if the chain isn't irreducible to start with, right?
You can define period of the state, but until
all the irreducibility is if and only if the period is same.
no.
Okay, so period of the chain can be defined even if it's not irreducible.
Yeah, you just need the period of the all the state.
Take 2 disjoint hexagons. So if you do a hexagon, take 2 separate hexagons.
Those are like manually created some kind of artificial examples, but mostly what we will be discussing will be good enough Markov chains to study. Because I'm not going to state a nice theorem which says that irreducible and empirical chains are actually good enough. Let's not do that. Okay. So now I will define again, sorry for long repetitions, something called the stationary distribution. So the main motivation for this Markov chain actually came from IID random variables because everyone started with IID random variables, but ultimately IID random variables are not so good to study because it's too special. That's why Markov started studying Markov chains, and we want to see the long term behavior. So you start a Markov chain, you let it run for long time, and after let's say 1,000 steps or 1 million steps, it kind of follows a typical pattern that you can observe, or you can predict at what probability it will be at x, at what probability it will be at y. So it kind of has an equilibrium structure. So if you in physics we have some idea of equilibrium. So if we leave a system, ultimately it reaches equilibrium. Here also we can have something like that. And what happens in equilibrium? At equilibrium, if it is at that position, it will remain that position for forever. So similarly for stationary distribution. So if I at one position of time, if I reach the stationary distribution, it will keep waiting at the stationary distribution forever. So let's say if I have the x naught to be distributed as now I want this distribution to be the stationary distribution. That is, if I once reach pi, I will remain at pi for forever. So what does this mean? This means that probability x naught equals to x is pi. This is just 4. And now let us find the probability x1 equals to x. And we want this thing to be same as pi, because I just told that if I once reach pi, I will remain at pi for forever. This can be written as this is from basic probability. And now I know this thing. I have this. And what is this thing? This is this.
X naught equals to
X naught equals to
Y. Oh, sorry. This is just px comma. And now I want this to be pi of x. Because if I reach pi, I will remain at pi for forever. And hence, this thing gives us the definition of stationary distribution. That if pi x is equals to this sum, then once I reach this distribution, it will remain at this distribution for forever. And you can check that this works not only for 0 and 1, but for any n and n plus 1. Because whatever we are basically using for here is n and n plus 1 over here, and then we are just using the definition of the homogeneous models. And that gives us this definition. And this seems to be a very nice definition because, again, this gives this. And if you want to write it nicely, then okay, I'll just erase this.
Should X and Y be switched over there? Like should
Yeah.
or shouldn't?
Here,
The sum.
mm,
You're summing over y.
Next one is.
It's summing over.
sorry. Okay, yeah. And let's just change this. Now it's okay, I guess. Yeah, it's okay. No, this I didn't change, I changed this one. Yeah. Okay, so sorry for that. If you have if the I want this thing to be same as in file, that was just okay, so I write it nicely. So if I consider this distribution pi as a row vector, which takes the probability of each state, I can write this thing as pi p equals to p is the matrix and pi is the matrix. So any distribution which follows this thing is a stationary distribution. And for irreducible change, the stationary distribution is in fact unique. So this is a change. Again, I am not arguing this thing, but you can check it out because we know that P1 is 1, so the cardinal of I minus P is, as I mentioned, 1, and you can check from there that if you use that this rank nullity theorem, then you can see that the distribution of P1.
Unique up to entry sum to 1.
Yeah, of course. This thing is very important because you want this thing pi x greater than 0 and summation pi of x equals to 1. Otherwise, it will not be a distribution. So that is a very special property. This is not just a right eigenvector or left eigenvector. This is much more special than this. Okay. So as promised, now let give a nice example is random of so does everyone know what is a graph? Not the function graph. So hopefully everyone knows, so I am not going to define that again. So let's take a graph with vertex at B and x at E. And what is happening in this graph is the graph. So let's say that we have this graph. And a person is sitting in one of the vertices and he starts walking on through the edges. And so what he does, so he is sitting here and he is looking at the adjacent vertices and he is moving there, he is randomly choosing one from them and he is moving there. So if he is sitting here, he can move here with probability 1/3. Because these are 3 and it randomly chooses among them. That is uniformly. And he can move here with 1/3 probability, 1/3 probability. And if he moves here, now he has 1/2 probability of going back to here or he can move here. And once I describe this, the transition matrix becomes easy to write. So if I know that I am at x, what is the probability that I will go to 1?
1/3.
This one is just a random number of and 5 steps, sorry, 6 steps. And you can try out any steps. This clear? We'll use that one now. Also, you can check the properties of this thing, whether this random mountain graph is irreducible or when is it irreducible and when is it aperiodic. You can make some guesses because, as I already told, that this irreducibility kind of imposes a connectedness in the model. And if you have a disconnected graph, you see that it's not reducible. Okay. So I will now define some random times. So whatever we were discussing previously, that n plus 1, t plus 1, whatever, all of them were deterministic. Now we will define something random. So I will first define fitting. So if you are at a position, a very natural question to ask is, after how much time you will move from x to 1? And there may not be any age here, or for random motion graph there may not be any age, or there may not be a positive probability to move directly. So you will take some steps. And it's a natural question to ask that after how much time you will move from x to y. And hitting time basically encodes that fact. And also, just look at this and you will be able to see that this time is not deterministic because it's random. Because you can move in 2 steps or you can move in 5 steps on anything. So it's very bad to ask for the random time directly. So it's better to ask for the expectation of that. So firstly I will just define and let's say what does this say? This is it says that first time I will reach x. That's why it takes a infinity. So if it starts at x, let's say tau y, maybe the first time it reaches 1. That's why hitting that. The first time it reaches 1. First time it reaches x. And now I will define something which is quite similar to this, but you will see why it is different. That is tau x plus. That is infimum t. The only thing I have changed here is this 0 and 1. So what does this say? So you will now think that these two are same. But this makes a difference when you start at x. What will be this time? Tau x. For this, if it starts at x.
0.
So this makes no sense. So it's worthless to ask for this time. So it's better to instead ask for this time, because what does this say? This says that you will escape from x and then come back to x. And what is the time taken in this path? And that is given by return time. And in fact, this is the first return time, and you can define more such return time, the nth return time, and I will define such return time in one of the problems that I discussed. But for now, just first return time results. Need up? And see now, I have not given you an explicit way to calculate the station distribution. So it may not be obvious. And also, you can't just believe that station distribution exists. You need to prove that. I will prove that. Yes, actually it does exist. Because this is not just a left triangle. It is more special. You need the entries to be positive as well as less than 1, and you need the sum to be 1. Okay. So now I will give them here. Actually, it comes as a corollary to many theorems that I am not going to discuss today. And just state it for given by so I'll explain what does this mean. This means that this subscript means you start at z. So this is the expected number of time taken from move to z, come back to z when started at z. And that's why now you see that why I defined this thing. Because if I just had tau z here, then it would have make no sense because it would be just z. And I'm not going to prove this, but this result is quite intuitive. And I'll try to explain that. Let's see if I. Yeah, this is the expectation. This is the expected time of tau z plus, provided it starts from z. Yeah, so this I will not prove again. I'll just give an indication of it. Let's see if that works. Am I going to? Because this is just
Like one question. So by xt equal to x, you mean it has positive probability. Probability xt equal to x is greater than 0. Is that?
no,
X
because
is a random variable. Right?
x is a random variable. So this is the first. That is why this is random. Tau x plus. Otherwise, it will not.
So it's not a number.
Not the number. It's a random variable. It's a random variable. And the random variable, randomness is imposed by that xt equals to. So, you run a Markov chain for long and long time. And as I have already told about the intuition of stationary distribution, the stationary distribution gives you the long term or the eventual distribution of the Markov chain. So what does that say? Pi of z equals to 1 by expectation of z tau z. That is, it says that the stationary distribution is inversely proportional to the time taken to return. So if there is a state where you will return many times, that is, this time is small, and that then you will return many times. Let's say the expectation is 2, then you will return many times, and hence this should be large, because if you look at the long run, then it's more likely that you will be at this step, because you will return to this step many times. Hence, this is the inversely proportional. And if it's too large, then you will rarely return to this step. And hence, it's more likely that if you look at the long run, you will not remain in the ZS. And that's why this inversely proportional thing comes. But in fact, you can of course prove it ZSly. But I'm just skipping that. So now I will give a nice problem that you can climb the break. And hopefully by the end of this lecture you will be able to solve this. But I'm just stating now and see it open solve. So there are n number of switches. N number of switches, and one of them is switched on. So there is this room with n lines. And these are the switches. And let's say this switch is on and the rest is on. Now a child has come and he is randomly clicking on the switches, and now as a probabilist I am interested to find the expected time for the room to go dark. That is, all the lights will be turned on. Okay. But of course, again, this is a random time. This is unique the expectation of this. And will discuss some models which will keep testing ourselves. We can start 10:30. Now we will discuss two popular examples that's quite common and many of you guys have already heard about this. That is Gambler's rule. So in a gambler's ring, you have a player playing with some amount of money. Let's say he has $8. Let's make it. Let's assume that he has given it. And now he is tossing a coin, and if head comes, he gains one more rupee. Head comes, and if tail comes, then he loses one rupee. And there is a finite sum of money available to the casino or whatever, and if he reaches here, then the game ends. Also, he can reach 0, that is, he will have no money to play with. In that case, he remains to 0, that is, he doesn't play again, and the game ends. So now, if you have this problem, okay, just write the name. So this is called the gambler's ring problem. An interesting question to ask is, after how much time the game ends, or if the game ends at a win or at a loss, and what is the probability, or what is the expected time for the game to end? And these two are really nice questions. And actually, you might think that why are we suddenly discussing some random problems from this kind of artificially created problems. But actually, when we have harder problems, we try to reduce them somehow to this kind of easy problem, and we already know the typical times and typical solutions of this, and we use that result to do even harder. So, as I told that, let's keep tau with the n. Take it for the game to end. So when does the game end? When it either reaches n or it reaches 0. Now I am interested in the probability that I will win. So what is that? Now at x tau, this can be either 0 or n. What is x tau? X tau is the position I will end. So it can be either n or 0. Now I am interested in what is the probability that x tau is n. So what is this subscript mean? This subscript again means that I start at k. I start at k, and what is the probability that I will win? And I am interested in another thing, that is if I start at k, what is the expected time taken for the game to end? And let's compute this probability explicitly. And once you get the probabilities, you will see that it's quite intuitive that those are the probabilities. So what I will do here is I will try to set up a recursion. So you are at 8 and you are moving here. Moving up. Now let us define this to be and now what is this thing? From k I can move to k plus 1 with probability half. So let's say I move to k plus 1. And now I want to find the probability that I will hit n when the game ends. And that is nothing but tk plus 1. And this should happen in n, that's why I have multiplied. Or it can move to k minus 1. That is, it can move to k minus 1 with probability half. And again from k minus 1, the probability that it will hit n is pk minus 1. And what is p0? And what is pm? You have a linear system of equation, you can just solve it and the solution will come out to you. And this is quite intuitive. So if you have more money, then it's more likely that you will do it. And if you have less money, like me, then you will. This is a tight answer. Okay. So you can also try out some typical solving analysis thing and this will probably the answer. And now let us find the, so this was this case. So we k square equals 20. And now let us find the expectation. Again, set up a recurrence. So I take fk to be this thing. And let's say you start from k, then and you can move to k plus 1 probability half, move to k minus 1 probability half. And now I can write fk as, so what is the probability that I will move to k plus 1? That's just half. And while moving, I have wasted one step. And now from k plus 1, how much time I will take to reach it? K plus 1. Or I can move to k minus 1. Again, at this step, I have wasted one step. That's 1 here. And from here, I will again take fk minus 1. That gives another equation. And we'll look at the boundary values, which is what is f0. That's just 0. Because if I am at 0, so what is the time taken in the game to end? That's just 0. And what is that? 0. Again, you have a linear system of equation. Solve it out. And then just check that these two solutions are actually unique, because this is a tridiagonal system of equation. Okay. Again, now this has a nice intuitive explanation. So if you are at the in between some 0 and 1, then it will take a longer time for the game to end. And if you have if you are at the edges, then it will take a lesser time. It will have something else. So it will take lesser time when you are at 0 at the edges, and it will take larger time when you are at 0. And that's like completely. Okay, I will now discuss another problem, which I will state here. And the only motivation of studying this problem is that I can solve harder problems in this. And that is the coupon collector problem, which is again quite well. So what is this? So a person has no job and he is suddenly collecting coupons, and he has n many coupons. He randomly picks one coupon and checks if he already has it or not, and keeps it back. So there are n many coupons. Just like the lunch and tea coupons, n many coupons. And now he picks one, n many distinct coupons. Okay, so all of them are distinct. So he picks 1. And of course, he hasn't collected any coupon this time. So this has to be a new coupon for him. So he writes down 1. And he picks another coupon. Let's say he gets back the same coupon again. Then he stays at 1. Otherwise, if he gets a new coupon, he adds 1 to this and he has 2. So he is basically counting the number of distinct coupons that he has collected. So it starts with 0 and goes till n. Now again the interesting thing to ask would be what is the expected time for the coupon collecting to n. But before that, let us look at the transition probability. So let's say if he at k, what is the probability that he will move to k plus 1? N minus k. Because he needs a u that he has not collected, that is n minus k. Or he can stay at k. Okay. So as I told, I want to find out this time between n distinct. And again, this is random time. I am not interested in this time. I am just doing the expectation of this. Yeah, it starts at 0. Okay. Now the interesting part of this problem is now coming because this will not have a typical solution like coupon selector, and it will have a different address. I will not set up a different recipe. So I will kind of break this time into intervals that we can measure, and then we will take that expectation because expectation is n. So firstly, let us define this time. Tau k as a time taken to collect k many coupons, k distinct coupons. Okay. Now, what is tau 0? Oh, tau 1. What is tau 1? 1. And what is tau n? Tau. Now I will write down tau like this. Okay. I break tau into intervals like this. Now, I will try to measure this interval. So, what does this say? So, what is tau k? Tau k is the time taken in this to reach k. And what is tau k minus 1? This time. So what does this show? Tau k minus tau k minus 1. This is the, once you get k minus 1 many distinct coupons, what is the time taken to get another coupon? Now we can try to measure this. How? So you have k minus 1 many coupons in your hand. Now you are picking up a coupon, you are checking if it's a new coupon. If it's a new coupon, it's a success for you. If it's not a new coupon, then it's a failure. And you are, what are you doing? You are basically contacting Bernoulli friends. And you are waiting for the success. And what is that random variable? German. And what will be the probability over here? This is just the probability of success. And what is the probability of success? N minus k. Now put expectation here. Expectation here.
Yeah, minus k minus 1
Plus k plus 1.
plus 1.
Now, tau 1 is a deterministic time, so the expectation has to be 1. And this should be, we know the expectation of geometry, right? And if you rearrange this will just come out to be. And this is quite good if you know this notation. This is just upper bounded by some constant times and so this gives us the expectation that I am calculating. And it's of course intuitive, it will have more then it will take more time, but this thing gives that it will rise not just polynomially but something. So now I think it's good. I think to take a break. Yeah, take a break. For 5 minutes. And doesn't depend on wherever because this is a collection of all things possible. Like, I just take x and y in or in x, and we look at the probability from moving from x to y. And it has all the directions, and that's why it doesn't depend on my prediction. Okay, so as I have written in the overview, I will discuss more kind of random walks on different structures. That's about also written in the abstract. So I will not discuss random now. Okay, so does everyone know about what is a group? Most probably yes. So I'm not going to define it. So let's say I have a group G. And I take an element from G, let's say H, and I assign a probability to it. This is the probability. And basically I am giving this G a distribution. That is summation that is each element of the group has some probability. That is the distribution on this G. Now I will define the transition matrix for a random walk in a group, and as I have mentioned during the break that the transition matrix kind of determines the Markov chain. So once I know this, I know what is the Markov chain. So this will just define the so what is basically doing? So you have G here, and from G you can go to many places by multiplying different elements of group, and if you multiply H, the probability will be mu of H. So there is nothing special about F multiplication. You can also define it through right multiplication, but I will just use it. Now let's see some examples. So the first example is the thing that we have already discussed. And what is the group operation over here? It's plus 1. And hence this cycle is just, the random of this cycle is just it's just a random of 1 Z6. And the operation over here is plus. You can do it any cycle Z. And what else? So one of the famous examples of group that we always study, the symmetry. So what is random permutation, you are going to another permutation, and you are going with some probability. So what are you basically doing? You are taking a permutation, you are going to another permutation. That is, you are taking n cards and you are shuffling it to move to another permutation. So if I can study random walk in SN, I can study random walk. I can study shuffling, and if I can study shuffling cards, then I can study shuffling genes, and which is exclusively used in biology and computational biology and many things. So just studying random walk in SN opens much more area to study. So this is an example. What else? Yeah. Let's take this. So what is this? This is a direct product of Z2. So if someone doesn't know what is a direct product, you can just think of this as n bits, and you add 2 bits modulo 1. That is, if you have 0, 1, 1, 0 and 0, 1, 0, 1, then if what is the addition operation here? You just 1, 0, 1, 1, 0, 1, and 1, 1 is 0, 0, 2. This is how you write.
1, 1 you get
0, 0, 1.
No. There is nothing called carry over. You are not adding binary bits. These are all bits. You add them modulo 1, modulo 2. So 0 plus 1 is 1, 1. 1 plus 0 is 1, 1. 1 plus 1 is 2, and 2 modulo 2 is 0. So this is the root vector, and now you will see why I am using this, because those guys who have already attended the colloquium that happened recently, they might find it familiar. So for n equals to 1, what are the possible things? 0 or 1. And from 0 you go to 1, or you move to 1, 0, or you go here. So let's first define this mu of it, otherwise it will be a problem. So I will use this EI as a standard basis vector, that is 1 at the ith position and 0 at the end. So I will give a distribution to this Z2n now. What will be the distribution? Mu of EI will be 1 by n, and mu of any other element of Z2n will be 0. Now for n equals to 1, what is the probability that I will move from 0 to 1? 1. If n equals to 2, then what are the elements? 0, 0, 0, 1, 1, 1, and what is the, so what is the basic vectors here? 1, 0 and 0. So what is the probability I will move from 0 to 1, 0?
Half.
What is the probability I will move from 0, 0 to 0, 1?
Half.
Half again. And what is the probability I will move from 0, 0 to 1, 1?
Nothing.
0. That's right. No edge. So I put an edge wherever I can go. And for n equals to 3, it will be something like a cube. And each probability is 1/3 here, 1/3 here, and 1/3 here. And those who can recognize this is nothing but just a hypercube. And also you can model this random walking group also as random walking graph, but the graph is this hypercube. And the adjacent edges are those vertices which are only one change. So you can generalize in 4 dimensions in that. And actually this kind of thing will be used in light shift problem. That was the intent. Now we will prove an interesting proposition. I don't know if there is a intuition to it, but for me it's quite nice. So the uniform distribution is stationary for a random walk on the circuit. This was quite non-trivial for me. I don't have any intuitive explanation.
Under some conditions on mu, under some irreducibility conditions on mu.
No, we don't need. there may be other questions. So let's just prove that. So what is the uniform distribution? Uniform distribution assigns equal probability to each of the elements. So that is, if I denote the uniform distribution with U, then U of G will be just 1 by 1 of all. So this is just a uniform distribution. And now, what was the definition of station distribution? This is a row vector and I multiply with the transition matrix. So let's say the transition matrix is P. So what I am doing is trying to find out this. Is this thing visible? So you know that P G comma 8G is mu of H. So what will be P G comma H? Mu
8G.
8G. So let's write this here. This one equals summation G belongs to G, U of G, mu H. What is U of G? So let's just replace this. U of G is 1 by. Now from G to AG inverse, this is a bijection. Okay. Now if this is a bijection, then I can replace this by G again. Is it clear? Because we are just summing over all G's. This is a bijection. So let's see if I can fit it here. This comes out to be summation G belongs to G 1 by mu of G mu of G. What is summation of mu of G?
1.
So this comes out to be 1 by. Now what is 1 by 1 G? This is just 2. This thing equals, sorry for this thing, I just wanted to put it here. So this thing equals, hence U is a station distribution. And now, once you know this, you know the station distribution of this thing. How many vertices are there in Hamilton?
2.
2 is bad. So what is the station distribution? 1 by 2. Now once you know this, by that theorem that we have already studied, we know the expectation that of return time, and that we will use in the light-sys problem. And I will just write down the answer over here. Hopefully you can do the thing. This will be the answer. Just check it. And if you have a random walk in SN, then also it's uniform. So if you shuffle the cards for long and long amount of time, ultimately the distribution or eventually the distribution will be uniform. This provided you define the random walk nicely. You need this properties too.
Yeah, actually there's some good intuition for this uniform distribution.
Yeah.
What you do is, let's say you take some group, okay, drop the transition matrix for this random walk. You will see what happens among the columns. What will happen is, if you look at the columns, you will actually see the same entries, but they'll all be sort of maybe possibly different positions. For example, you might see like 3 1 by 3s in a column. In the next column, you will also see 3 1 by 3s, but then they may be interspersed. So what you notice is that all the column sums are actually the same, and in fact, they are all sum to 1. So such a matrix is actually called as a doubly stochastic matrix, and every doubly stochastic matrix has the uniform distribution as a case matrix. And under some obvious conditions on mu, your graph is irreducible, so you automatically get that return type.
No, random walking group is need not be irreducible.
No, it need not be, because it depends on mu.
Because the support of the mu is not generating set.
Correct. So you need support of mu.
Yeah, so as promised, I will now discuss another kind of random walk in a different structure. And this is the first time we are going to discuss some finite. Okay, this G was also finite. This is the first time I am going to discuss something. How to do that is random walk on. Again, this is very popular. This is one of the first random walks I will introduce to. So what is happening here? So you are in the Z line. The person is standing here, and he is tossing a unbiased coin. If head comes up, he moves right. If leg comes up, he moves left. And this is a simple random walk. You can make it more general by putting biases on the coins. So and I will just discuss a simple thing. And from -1 you can again cross it 1 and you can go. Now the interesting thing about this, so if you start at 0, what is the probability that it will return to 0? Infinite. And that probability, I don't know, it was quite surprising for me. It will be surprising for you guys. This probability comes out to 1. So if you start at 0, eventually, after some time, the probability of returning to 0 in finite time is 1. So let's prove that. So I will denote a random number in Z with Sn.
So it's for 1 by 1 case only.
Sorry?
For P and Q it won't hold.
No, for P and Q it will not. Then it will be something else. Actually, the explicit expression for P and Q is, I guess, this thing. If I remember correctly. Whatever. So let us denote the random occurrence here with Sn. So I will count the number of times it reaches 0. So this 0 means that it starts with 0. Can it be 0 in odd number of steps? And this is just a sum of randomization variables. Okay, whatever. This is sum of random variables which takes half -1 probability half and 1 is probability half. Then if it wants to reach in n number of steps, then it would be like it needs k plus 1s and k minus 1s. And it would be so it has taken 2k steps and it needs to have k plus 1s and k minus 1s and each which is happening with probability half, and that is
That's 2 kg is K, right?
2k is k, yeah. So now I will count the number of times it comes to 0. And what is that thing? That will be just indicator of Sn equals to 0. Again, this is random. We are not interested in this. We are interested in the expectation. You put the expectation here. What will be this thing? This will be just summation n probability SQL. I'm just writing it SQL because of course you cannot write it. Now, if you use Studying's approximation here, or some kind of approximation, do you guys know Studying? Okay, we'll just write it. Hopefully I will get the constants right this time. This time I write answer will be wrong. But this n to the power n and n to the power half is, that's what matters most. And if you use Studying's approximation here, then you will see that this thing is approximately 1 by and if this is n to the power 1 by n to the power half, then this thing diverges. Right? Now I will count the number returns to 0 in a different way. Now I will define what I have already mentioned once, the nth return. So what does this say? You know what is tau 0 of 1 is. Tau 0 of 1 is plus. So once you know the first return time, you can define these things. So recursively, you will define it to the second time it returns back to 0, and third time, and so on for n. Now I will, as I have already told, I will count the number of times it returns to 0 with the help of this. And what will be the count? It will be just summation over. What is this thing basically counting? Counting the number returns to 0 in finite time. And this is what we have counted here in finite time. And again, this is random. I take the expectation of this. What is this? This is the summation n. It will be 0. And now here comes the interesting argument which will be used, which is used actually in probability a lot. In fact, it can be generalized, but I will not mention that. So if you are at 0, you want to return n times. But once you return to 0, it doesn't matter whatever happened in the past. The only thing matters is that you are at 0. So the probability you will return in the first time is probability 0, tau 0 plus less than 0. And once you are 0, you will start a new beginning. And what is the probability you will again return? That is again probability 0, tau 0 plus less than 0. And what is the third time? Similarly. For n times, this will be just this geometric series. And this series is equal to that series. So this, if that series diverges, this should also diverge. And if you want this to diverge, then you need this to be, the modulus of this needs to be greater than equals to 1. However, this is probability, hence this has to be 1. Just keep in mind this argument, because for the Z2 and Z3 case, I will not be doing this again. I will just find out the Sn probability of returning nth step, and I will just look at this thing and tell that if it's divergent or not, and that will conclude this, because this thing stays same for Z2 and Z3. I will try not to erase this. Let's see. That works.
We have to that part.
Yeah.
So that's the geometric series, and then y is equal to 1.
Yeah, so this is geometric series, and what are we basically counting? We are counting the number of returns to n, 0. And there also we are counting the number of returns to 0 in finite time. Both are finite time. And that series diverges. And that series exactly equals this series. Because we are counting the same thing. So this has to be. So let's do the case of Z2. Z2 has a special structure for which the problem becomes a bit easy. And you will see why that doesn't work in Z2. The definition is quite same only, because you just move in the 4 degrees of freedom now, and with probability 1/4 each. And yeah, so now I will model this random walk on Z to a little bit different. So let's take 2 random walks on Z, and these 2 are independent. Okay, so 2 are here. Now, what is the probability will move to 1, 1? You need this to move to 1. You need this to move to 1. What is the probability in that? 1/4. These 2 are independent. This is 1. And what is the probability to move here? 1/4 again. It will move here 1/4 again, 1/4 again. So basically, it is moving along this parallel to the lines y equals to x and y equals to minus x. And you will get something like this. This is exactly the random walk in Z2 but rotated. So if I know the probability of return in this model, I know the probability of return in Z2. So let's find out in here, and that's too easy because 0 is probability 7 0 square. Now what is this? We have already found out. Now that one was approximately 1 by root 10. So this will be 1 by 10. Again the series will be divergent. And hence this will be. Now you might have a feeling that this same thing will continue to hold in Z3 and Z4 and so on. And unfortunately that is not the case. And in fact for Z3 and for higher dimensions, the probability to return to 0 is less than 1. So hopefully now you are comfortable with this argument. So I will erase this because Z3 will take more time. Because this kind of argument will not work. So why this argument work? This argument work because you can move here with probability 1 by 2d and these are dimension. And these are, we can couple two things. Basically this is a couple. We are taking 2 independent random walks. So if I take 3 independent random walks, this, the probability of moving here and here, that will become 1 by 8. But we need it to 1 by 6. So it only, this argument only works for relation. So you have to work with it more in order to use the relation. So again the definition is same. You move in each basis vector, standard basis vector, in probability 1. And now let's again write down this probability. Because this is the thing that has been happening. So this is the 0 vector quality. Now what is this thing? So if you start at 0, if you want to return to 0, you need to take equal number of steps in the positive z axis, positive negative z axis, as well as positive y axis, negative y axis, and positive x axis, positive y. So let us assume that it has taken j steps in positive and negative x axis, k steps in positive and negative y axis, and what are the number of steps left with us? 2n minus 2j minus 2. Okay. Now it will again, we need to divide them equally in positive and negative direction. Now it is the rearrangement problem. We have done it in S2. It's just in factorial by factorial. So this j and k can be anything. So we sum over all the possible j's and k, and each of these has probability 1 by 6. 1 by 6. Oh, sorry. 2 equivalent factorial and the square root because there are positive and negative ratios. Now I will manipulate this term and massage it into this thing. 1 by 2 n summation 2 it's okay. It's cancelled. Now, now I will use this thing, which you can just take it out. So AJK is this term, and this the sum of the squares of this term is bounded by this thing. You can just take it out for, of course, for this thing has some special properties that you need to use. It's not true. So I will just use this and just write it down. Not summation, I will replace this with max. Now, when does this term achieve maximum? Again, I will leave small details to you guys. This achieve maximum when these three are all equal. Of course, it will not be possible for all n, but quite close. So, for large n it doesn't matter. So, I will just replace them by n by 3. But before that, I will Stirling's approximation over here. So, I will just see my notes. I don't have to mess this up. Is that's a lot of work, and this comes out to be some constant times q to the power n. Right. Yeah, I think that's right. So once
When you put JK and by 3.
yeah, JK n by 3. Yeah, exactly. Oh, sorry, I forgot to tell that. So this happens when JK I put n by 3 because otherwise it's not possible. Because I'm just interested to find an assignment. So hence, this thing is this one times this one. What is this one? It is approximately 1 by 10 to the power half. And what is this one? This is 3 to the power n by n, and there is 3 to the power n here. So it gets cancelled. There is 1 by n. This is what is this? It's constant. And hence the probability has to be less than 1. That's why there is a famous line that says that a drunken man will always return to his home, but a drunken boy will not. It doesn't work. And for Z2, Z greater than 3, there is the induction argument, but I am not going to waste more time in these things.
Induction argument for what? Inductive argument for
Yeah, this argument. So basically, you can project the Z4 to Z3, but not this needs to be described actually because this is not quite clear. I'm just giving an intuition. So you need to project Z4 or ZD to ZD minus 1, it means to continue, and you know that ZD is transient, or it never, so there is a less than 1 probability it will return to 0, and it works out for all the things.
Apparently, we are only getting half in the scoring. Does that hold in general?
Yeah, so this one?
No, for the angle what we were. So like will it for 4 dimensional be x square and
Yeah, possible.
No, it's true.
I think it's true. Because you are again doing this same area and but the induction argument is quite nice because this needs a lot of work. Once you have done this work, you just do this. Yes. Now I will digress to a new topic, that is sampling and random sampling. Not the sampling that you guys have done, it's just IID, but these are samplings which are difficult to do. Have some time. See how much I can do. So let's say, does anyone have a doubt in this? No. Let's say you have a graph. Now you want to color this graph. So you put colors in such a way that the adjacent vertices have different colors. Now let's say you want to generate a random coloring. For some reason, I don't know why, but you want to generate a random coloring. But the problem is, if the number of colors are huge, then the number of possible colorings will be huge. And although the number of possible colorings rises polynomially, but listing all of them out, it is too difficult. So if you want to pick a random coloring, you need to list all of them out and choose one of them. And that becomes a too difficult job for a computer to do. Right? So that's why we use some randomized algorithm. So just like we have P and A problems, we have something called RP also. But I will not discuss that. So I will discuss how to choose a random color. And that will be that will be done through Markov. So let us do this for general, that is something called Glauber Dynamics. So you have a set, you have a graph, let's say B, and you have a set S, and you are looking at the functions from B to S. You can just think it as a vector also because everything is finite but all the sets are finite. Now you take a subset of this thing and now you want to sample from X. It may be uniform, it may not be uniform, it can be any distribution. So can I describe a nice enough Markov chain such that the stationary distribution becomes the distribution that we want? So if we can do that, we can run the Markov chain for a long amount of time and eventually we will know that we have an approximation of that distribution. It's not perfect. And that works for more or less many cases. And now, so how do we describe this Markov chain? So what I will do, I will first choose a vertex randomly. So choose a vertex uniformly. And then I will look at all those vertices or all those configurations. So what we basically have, here we start with a configuration. We don't start with a vertex. We start with a configuration. We have a function already in the graph. So we already have a coloring, let's see. And now we want to move to a new coloring. So we already have a configuration, and I want to move to a new configuration, and let's say I have picked the vertex as P, and I will look at this set, that is all possible configurations y such that y of w equals x of w for all w not equals to. That is, I move to only those configuration that is same everywhere except at V, or it may be same at V also. I can remain in that position. So what are you basically doing? You are choosing a vertex. Let's say I have chosen this one, and now I keep everything same, and I change this, and I change this with certain probability. And if I do that, this Markov chain will take me to stationary distribution in what? And how should we change? We should change it like this. This may look quite convoluted, but explain this is easy. So what are you basically doing? You are conditioning on this event. So basically, you have chosen this V. Now you look at all the possible configurations which are here, and now you choose that configuration, some configuration with respect to this probability distribution path. So this is the probability distribution that you want. You want to sample from X with respect to this distribution, and hence you use this, and you will find out that if you write down the transition matrix, you can write down it easily because it's just 1 by V times this thing. And if you write it down, then you will see that this pi is actually the stationary distribution. And it might look quite calculated. I will show you the random coloring example. So, and I have discussed this in general because for random coloring we don't want all the possible colorings. We want the proper coloring. That is those colorings such that the adjacent vertices have different colors. That's why I have taken this X. And if we want to sample uniformly from the random coloring, that is, we want pi to be uniform. And this X will be the set of all possible random colorings. And hence we can use the same algorithm, and eventually we know that this will converge to the stationary distribution, or it will go close to the stationary distribution, that is the uniform distribution for random colorings. Let's just write it down. So what we want? We want a uniform sample from the random colorings. That is, pi is uniform. And this is enough to describe the whole thing. And also the X. X is the set of proper colorings.
You will be repeating this process, right?
Yeah, we will be repeating this process. This will be a
vertex and
choosing vertex, moving to different configuration, choosing again another vertex, moving to a different configuration. And if we continue this, we will generate for random coloring case, we will generate another proper coloring, and we will continue this, and ultimately we can generate a nice uniform sample from the proper. This works out quite well, and you can give much better bounds, after how much time it will reach a stationary distribution. And this is the random coloring model. Is this thing clear? This seems to be quite convoluted, but this just is that it moves to the configurations by changing the this thing is conditioning this.
For this convergence, we require the condition of atriotic as well as irreducible.
Yeah.
So is it
This one. No. Glauber Dynamics. For general Glauber Dynamics, I guess you can't say. Because you can choose the pi such that it may not return to x. But for random colorings, I'm not sure.
So we pick a vertex uniformly at random,
Yeah.
and then we look at that set X of small x v,
Yeah.
where everything except v is the same, right? And then we pick
Not except v, because it can be same as v also. It can return. Yes. Then in that case, if I assign that x to be this pi to be uniform, then in this case it returns.
Okay, so what is that set again? Can you explain what that set
Yeah, this set. So what are you basically iterating on? You have a configuration, you have a function, and you are moving from one function to another function. So you have a configuration on the graph. You are moving from one configuration to another configuration. So you are choosing a vertex. You are looking at the all possible values it can take. You are changing that vertex to that possible value. And what is the probability in this that changing? That is governed by this pi.
So we already know pi.
Yeah, the pi is the stationary distribution you want.
Okay.
So if you just write down the transition matrix, you will see if you multiply pi times p, then you will get pi.
So it is like we have a graph with all vertices colored, and then we pick a random vertex, and then we pick a random color and change all other vertex.
No, we don't change all the other vertex. We keep all the others same. We change that vertex, whatever we have chosen. That's why I have kept all the others same except v, and then I change that. And how I change v, that is governed by this. Is it clear? So I have a few minutes left with me, so let's see if I can. This is nice, nice model which resulted in 1 Nobel Prize and 2 Fields Medal. That is the Ising model. The Nobel Prize was by Parisi last year in physics, and this year Hugo got the Fields Medal for his work on Ising model. And 8 years back, Spinov had some results for it. So in Ising model, before describing Ising model, it is described as more general model. That is, I take this. Now I have a graph. The graphing is constant. I only change this thing. That is -1 and 1. And my x is all the functions. Now I am not taking a proper subset. For this it was a proper subset. But on this it's not a proper subset. So basically you have a graph. You have some edges. And to each vertex you are assigning +1 or -1. So it's kind of a spin for the vertex. It assigns +1, +1. So sigma of p is +1 or -1, and this is called the spin of a vertex. This kind of models are called spin systems, and I will discuss a special type of spin system, that is the Ising model. And this can be interpreted more physically like magnets. So you can think the +1 as the north pole pointing towards you and south pole pointing towards the planet. So +1 is like this, -1 is like this, -1 is like this, and all the other -1. You can think of this as magnets. And now I will define the energy of the system. Again, these are all motivated from physics, but we don't need any physics to study all this. It will be quite mathematical. So So again, we are moving on configurations. We are interested in the configuration, not the vertices. We already have a configuration and we are defining the energy of that configuration. So here is the energy. Now again it's quite intuitive because if two adjacent vertices are in the same direction, the energy will be negative. And by physics we know that a system always wants its energy to be given negative. That's why it will always try to, I will define what does try mean. So it will always try to be pointed towards the same speed, such that it can reduce the energy. And here, the distribution that was uniform in the random circuit, here it is not uniform. In fact, we will use the gauge distribution that is 1 by 0 square due to r minus. Hopefully everything is right. So z of beta is nothing but a normalization constant, and I just define this e to the minus beta.
What is exactly beta?
Yeah, I will explain. So beta is a parameter over here, but physically it has a meaning. So beta is proportional to the inverse of temperature. Now let's say what does it mean? So if temperature is too high, let's say temperature tends to infinity, then what happens? Then beta is too small. If beta is too small, what about this value? This value is quite close to 1. So but this h of sigma may be positive and may be negative. So it gives more bias towards the low energy states, and it gives less bias to the high energy states. That's why I was talking about this. It will try to align to the same speed. When is the high energy? High energy states are the states where the spins are in opposite directions. And if T is too small, then this uniform, this distribution will become uniform.
Other way around.
Oh, sorry.
T going to 0 leads to
Sorry. This is inverse thing. Yeah. So if T tends to infinity, then this becomes uniform, and if T tends to 0, then it gives high bias to low energy.
So you are assuming h of sigma is less than.
No, h of sigma can be positive and negative. Yeah.
This mu is a
Mu is a distribution.
so you are assuming h of sigma to be positive.
No, it doesn't matter. This thing is there to normalize it. So now if you want to simulate this model in actual computer by hand, then again you will use the Glauber Dynamics. That is, you choose a vertex V at random, and then so you pick a vertex V at random. Let's just write the spatial distribution. Sorry, transition matrix. So you pick a vertex V at random, and now you look at the possible positions in that vertex. What are the possible positions? +1 and -1. And you want it to be distributed with this product. So it is nothing but sigma. Transition matrix, and you can simulate the model through this transition matrix, and you can of course simplify it down because you can check that the only thing that changes is the v from +1 to -1. So you can change. No, z of beta will get cancelled. It should get cancelled, right? Yeah. There will be 1 by z of beta here, 1 by z of beta here. So again, many things will get cancelled actually. You can write a much better explanation, better thing to this, because the only thing that is changing is that. Yeah, is it okay? Okay, that's it then. That's it about Ising model, and hopefully you like that. If you have any questions, please feel free to ask. the primary reference is a big daddy book, Markov chains. And it's available free in internet, and it's one of the most famous book of Markov chain and most populated anyway. And I have taken some things from internet. That's of course the history I have told, and there is this lecture notes in some Wisconsin mansion, I guess. I don't remember the exact reference. I can send you the link if you want. And from there I put the random options. And all the other things are available in the first 3 chapters. And yes.
What exactly are we calculating the variance P of sigma?
Yeah, this is the transition matrix. From sigma to sigma. Okay. Is it good? I guess it's correct.
What exactly that Z of beta does to
Z of beta is just a normalization of the system. It's called partition function in physics. I don't have it. That's correct.
Are there any more questions? So, thank you for the one talk. I hope all of you liked the talk very. So, this was possibly the last talk for this semester. We'll continue again next semester, and we'll also be meeting some of you in the midterm.